Hello students, and welcome back to Chemistry A. I'm Miss Sleight, and today we're going to be talking about the trends of the periodic table. There are 5 trends that we're going to be focusing on this chapter. They are atomic radius, ionic radius, ionization energy, metallic character, and electronegativity. These aren't the only trends that you'll find on the periodic table, they're just the ones that we're focusing on for this chapter. First off is atomic radius. Now, atomic radius is defined as half the distance from center to center of two like atoms that are bonded together. So if you look down at the picture there, they have 2 chlorine atoms bonded together. The distance from center to center on each of those is their atomic radius. Now, for our trends in atomic radius, you should see that atomic radius increases as you go down a group and decreases as you move from left to right across a period. Let's talk about a little bit more about why that is. So first off, we have the Bohr models and electron configurations for lithium and for sodium. We can see that the atomic radius for sodium is much larger. And the reason why your atomic radius increases as you go down a group is because you're adding more energy levels. If you look at lithium, it just has 2 energy levels, as opposed to sodium that has 3 energy levels. More energy levels means there's greater electron shielding. Electron shielding is the phenomena where if you add more energy levels, the electrons in those outermost energy levels feel less and less attraction to the nucleus, the farther away that they are from it. Let's think about a little metaphor to help us kind of think about this a little bit more. Let's say I'm an electron. I'm the little red electron on lithium here, and I'm attracted to the nucleus. But instead of the nucleus, let's pretend the nucleus is my celebrity crush, Hugh Jackman. So currently, there's just 2 other electrons between me and Hugh Jackman. So I'm going to experience a pretty strong attraction to Hugh Jackman. However, if we look over at my situation in sodium, there are 10 other electrons between myself and Hugh Jackman. So I'm not going to feel nearly as strong of an attraction. And that's basically how electron shielding works. Let's talk about the trend in atomic radius as you move across a period. You'll see that atomic radiuses get smaller and smaller. Here we're comparing lithium, carbon, and fluorine, who are all in period 2. So atomic radius decreases across a period because the more protons that are in the nucleus, the more attraction the electrons feel to the nucleus. So they just want to get a little bit closer to the nucleus. You should also notice that in the same group, your amount of electron shielding stays the same. So there's still the same number of energy levels in each of these atoms. It's just there's more and more protons in the nucleus as you move across the period. Let's kind of think back to my celebrity crush metaphor again here. All right, so in lithium, let's say in the nucleus of lithium, let's replace that with 1 Hugh Jackman. So me, as an outermost electron, is going to feel some attraction towards Hugh Jackman. But if in carbon there's 2 Hugh Jackmans, I, as an electron, will feel an even stronger attraction, want to get in a little bit closer. And in fluorine, let's say there's 3 Hugh Jackmans in the nucleus. I'm going to feel an even stronger attraction to the nucleus and try to get closer to it. And that's the main idea with why atomic radius decreases as you go across a period. Now let's talk about ionic radius. Now an ion is just an atom that has gained or lost electrons to become charged. Now the reason atoms tend to gain or lose electrons is because they want to have a full valence energy level, a full valence shell, meaning they're going to gain or lose electrons to fill up that outermost energy level. For example, let's look here at sodium. Sodium has just 1 valence electron. So if it were to lose that electron, it now has a full outermost energy level. But if it loses an electron, it's losing a negative charge. So the atom now will have a positive charge overall. Ionic radius tends to decrease as you move across a period and increase as you go down a group. But you will see that there's kind of a little jump in the ionic radius somewhere around group 13 or so. And we'll talk about why that is. So first off, ionic radius increases down a group for the exact same reason that it does in an atomic radius. You're adding more energy levels. The atom gets bigger. It also decreases across a period for the exact same reason that an atomic radius does. You aren't changing your number of energy levels. Your electron shielding is remaining constant, but there's more and more protons in the nucleus, so your outer electrons feel a greater and greater attraction and want to move closer to it. So let's think about positive ions here. Our example here is lithium. It has one valence electron, so it's very easy for it to lose that electron, and then it has a full valence energy level, because energy level 1 can only hold 2 electrons, and it becomes a +1 ion. But because it lost that 1 electron, it lost one of its energy levels. So it's going to become smaller than the neutral atom. And this is true for all positively charged ions. Positively charged ions will always be smaller than their neutral atoms because they're losing electrons to lose an energy level so that the next one is full. It's kind of the opposite with negative ions. So if we look at fluorine here, fluorine has 7 valence electrons. It only needs to gain 1 in order to fill up that outermost energy level. So when it does, though, it's adding another negative electron. Adding another negative charge causes there to be greater repulsion between the other electrons. And that's going to make the electrons move away from each other a little bit more, and thus make the radius of the ion larger. And this is true for pretty much all negatively charged ions. A negative ion is always going to be larger than the neutral atom. Now let's talk about ionization energy. Ionization energy tends to increase as you move across a period and decrease as you go down a group. Ionization energy is defined as the energy required to remove an electron from an atom or ion. Now, we're going to be talking about first ionization energy exclusively, and that's just the energy to remove the first electron off an atom. There are slightly different things that you see happen when you move into second ionization energy and third, and so on, but we're going to be focusing on just first ionization energy in this chapter. So if we look at lithium, its outermost electron only has 2 other electrons between it and the nucleus. There's very low electron shielding. So that electron is going to feel a strong attraction to the nucleus, and it's going to be held tightly, we could say, by the atom. However, in sodium, its outermost electron has 10 electrons between it and the nucleus. So it's experiencing much greater electron shielding. And so that electron is going to have a weaker attraction with the nucleus. So the atom's going to hold on to it more loosely. So the reason that ionization energy decreases as you go down a group is because when the valence electrons are farther from the nucleus, they experience less attraction with the nucleus. That's the idea of electron shielding. And if they experience less attraction with the nucleus, it requires less energy to remove those electrons from the atom. Now let's look at ionization energy across the period. So again, we have lithium. Lithium has only 3 protons in the nucleus, so it has a relatively low nuclear charge. So its outermost electron, compared to the others in the period, will be held more loosely. However, In fluorine, fluorine has 9 protons in the nucleus, so that's a much higher nuclear charge. So its outermost electrons will feel a much stronger attraction with the nucleus. They're held more tightly. So as our nuclear attraction increases when you move across a period, the outermost electrons experience more attraction. They're held more tightly. And that means it's going to require more energy to remove those electrons than it would for others. Now let's talk about metallic character. Metallic character is the ability of an atom to lose its valence electrons. And metals tend to do this more easily because they have very loosely held valence electrons. So metallic character decreases as you move across a period, and it will increase as you move down a group. So the most metallic element is going to be francium, because it's in the far bottom left corner of the periodic table. Lastly, let's talk about electronegativity. Electronegativity is the ability of an atom to attract electrons in a chemical bond. This is not the same as the ability of an atom to gain electrons. This is not the same thing. This deals exclusively with how strongly do they attract electrons when they are in a bond with another atom. And you should see that electronegativity in general increases across a period and decreases down a group. However, if you look at our little scale here, you'll see that helium is not the most electronegative element. Fluorine is. In fact, most of our noble gases do not have any electronegativity at all, and that's because they are so unreactive that they do not form bonds with other elements. Krypton and xenon are the only exceptions. They do have some electronegativity because on rare occasions they can form chemical bonds. But the rest of your noble gases do not, which means the most electronegative atom is fluorine. And that wraps up our discussion of periodic trends. If you haven't done so already, make sure you fill out the trend arrows on your latest periodic table. And I hope you have a great rest of your day.